Hello everybody and welcome back to M Cubed, Mahi's Magical Math. Today we are going to be solving the last set of problems from the Math Kangaroo Level 3-4 2024 exam. So let's dive right in. Okay, problem 18. Lucy weighs some blocks. A rectangle and a circle together weigh 200 grams. A triangle and a circle together weigh 100 grams. A rectangle and a triangle weigh 240 grams, and we need to find out how much do the three different blocks weigh together. So, in this case, we want to note some patterns. First of all, in these two expressions, the circle is common, and we see that the grams differ by 100. So, the rectangle and the circle make 200 grams, but the triangle and the circle make 100 grams, which means that the triangle has to be 100 less than the rectangle. So let's write that down somewhere. So we know that rectangle minus 100 equals the triangle, which means if you add 100 to both sides, the rectangle is the triangle plus 100. So rectangle is triangle plus 100. So now that we know this, let's plug it into the equation that has a rectangle and a triangle, and we can figure out the value of one shape. So over here we know this equation. We know that a rectangle plus a triangle equals 240. And we know that the rectangle is a triangle plus 100, so we can plug that in, which means we get to 2 triangles plus 100 equals 240. Subtract 100 from both sides, and we know that 2 triangles equal 140, and that means one triangle has got to equal 140 divided by 2, which is 70. So now that we know that one triangle is 70, all we have to do is plug it in to any of the remaining equations. So if the triangle is 70, then according to this, the circle has got to be 30. And if the circle is 30, then the rectangle has to be 170. And that makes sense, because if you plug this triangle equals 70 up here, 70 plus 100 is indeed 170. So adding all this up, 170 plus 30 plus 100, 170 plus 30 plus 70 is A, 270. So the answer for 18 is A. Let's move on to 19. There are 60 students on a trip. When they line up, the colors of their reflective vests follow the pattern: yellow, green, yellow, green. The colors of their backpacks follow a different pattern: red, brown, orange, red, brown, orange. How many students with a yellow reflective vest also have an orange backpack? So let's think about this. Take it in. There's this pattern that they've given us that we need to use to solve the problem. We know that, and I'm going to color code this right here. The vests are yellow, green, yellow, green, and I'll go one more, yellow, green. Their backpacks are red, brown, and orange. And then we'll do that again, red, brown, and orange. Okay, now that we have this, let's see if we can see a pattern. We need the yellow reflective vest and the orange backpack. That happens here and not another time in our little sequence. But let's notice something. This sequence has a repetition of 3 of these groups and 2 of these groups. So that means in each group of 6 students in total, there's going to be 1 student who has a yellow vest and an orange backpack. So how many groups of 6 go into 60? 10. Which means if 1 student in each group has the yellow vest and orange backpack, and there are 10 groups, then E10 is the correct answer to this problem of students who have a yellow reflective vest and an orange backpack out of the 60 students on the trip. So this is a super useful strategy for these type of problems, to just do a tinier problem, find a pattern, and then see how many times that fits into the bigger problem. Okay, moving on to the next question, which is kind of similar to problem 18. In the following calculations, the same digits are hidden under the same figures. Different digits are hidden under different figures. What is the value of triangle times circle times square? Okay, this is a very important word right here. Digits. Digits. These are not numbers. These are digits. So we know that triangle plus triangle equals square circle, which means that's a number. That's a 2-digit number. Circle plus triangle equals square square. And we need to find the product of all of them. So take a minute to think about that. How are we going to solve this? Well, let's look at the square square. This number is the same digit twice, so it's like 1, 1, 2, 2, 3, 3, 44, 55, etc. But it's the sum of 2 single digits. So it can't be like 55 or 44. It's got to be something small. So the 2 smallest are either 11 or 22. Can 22 be expressed as the sum of 2 single digits? No. The largest you can get is 9 plus 9, which wouldn't even work since these are 2 different shapes. And that only gets you to 18. So 22 is definitely not going to work, which means the squares have to represent the number 1. So let's write that in. Now, suddenly things are looking a little better. We know that this could be any 2 digits. It could be 2 and 9, 3 and 8, 4 and 7, 5 and 6. We don't really know. But we do know that whatever the triangle is, times 2 has got to equal 1 and then a circle. So what digit times 2 equals a 2-digit number? Well, 5 times 2 equals 10, but we can't have the circle as a 0. It's got to be an actual number, because otherwise 11 would have to be the triangle, and 11 is not a digit. So it's not 5. We can have 6 times 2, which equals 12, 7 times 2, which equals 14, 8 times 2, which equals 16, and 9 times 2, which equals 18. So now this is a small enough problem where you can just plug these in and see if they work. If the triangle is 6, does this make sense? Nope, 2 plus 6 is 8, not 11. So it can't be 6. What if the triangles are 7? Oh, this works. 7 plus 4 is 11. So you could try the rest of the answer choices just to make sure you're not missing anything. But this is clearly the answer. So now, finally, they're asking us what is the value of the product of all of these. So 7 times 4 times 1 is 28, D. So the answer for problem number 20 is D. Let's move on to problem 21. It reads, there are exactly 2 frogs in each row and each column. The frogs decide that 2 of them will jump to a neighboring empty cell at the same time. Neighboring cells have a side in common. Afterwards, there still will be exactly 2 frogs in each row and in each column. In how many ways can the frogs do this? Well, this is a problem where just going and looking at possible answers is probably the fastest way to do it. So let's start with the frog in the top left corner. This frog can only move sideways right now. And if it moves here, then there will be 3 frogs in the middle column. So then this one has to move to this empty space. That is one combination that works. So we have 1. Now, oops, let's erase. Now this frog, it could also move down if this frog moves. But then there are going to be 3 frogs in this row if this one moves down, and we don't want that, so that is not an option. So we've already exhausted the number of ways that this frog can move in the top left. So now let's try this middle frog. Well, if this guy moves down here, then this guy has to move up. So that's way number 2, and we can cross out A. This frog can also move sideways over here if this frog moves up. However, that's not what we really want to do, because then there would be 3 frogs in this row. So let's look at the center frog. If the center frog moves up, then there will be 3 frogs in the top row. So this frog must move down. It's the only frog that can move down. And then you would have 2 in the first row, 2 in the second row, and 2 in the third row. So that's our third way right there. B is not an answer. So we looked at this frog, and this frog. Now let's look at this frog. If he moves to the left like this, then there will be 3 frogs in the center column. And the only way to counteract that is to have this frog, middle frog, move here. But we already counted that. This frog could move here as well, but then there would be 3 frogs in this row. So that's not going to work. So we've already exhausted all of these guys. Now, let's look at this one down here. If he moves sideways, then this top frog has to move here. But we already looked at the top frog. So we're done with this guy too. Now finally, this frog. He can move up. And then this frog has to move down. So we already counted that one as well. Let's check our work to make sure we didn't miss anything. Because even though we looked at all of the frogs, we should still look over it again. Because as 2 frogs move up, like they can move up together and move down together as well. So we should make sure. If this frog moves up and this frog moves down, we already counted that. If this frog moves sideways, this frog can also move sideways, but then there would be 3 frogs in this column. So that doesn't work. What if this frog moves up and this frog moves down? Ah, now that is a good idea. Because what we were doing before is making sure that when there were 3 frogs in a row, that we moved one of them. That's why this possibility didn't come up. But when this frog comes up here, there's only 1 frog in this row. We need to balance that out by moving this frog down here. So that is another possible way. So now we're at 4. And we can say that we've exhausted all of these options because we've looked at times when there are 3 frogs in a row or column, and when there's only 1 frog in a row or column. So the answer here is 4. And for this type of problem, it might seem that I solved it really slow, but in the actual exam, it would go much faster. Just make sure that you keep track of what you've already completed and don't overcount. Okay, number 22. The figure below shows a honeycomb with 9 cells. There is honey in some cells. The number in each cell shows how many neighboring cells contain honey. Neighboring cells have a side in common. How many cells contain honey? So don't look at the H's over here. Those don't matter. Let's reread the problem and highlight important information. So there is honey in some cells. The number in each cell shows how many neighboring cells contain honey. So like, if this one says 1, then that means 1 neighboring cell contains honey. How many cells contain honey? Well, first let's start with stuff that we know. And I'm going to label honey with blue just because labeling it with yellow wouldn't really work on this yellow honeycomb. So let's look at this 2 over here. It only has 2 neighboring cells, which means both of them have honey. So this one has honey, and this one has honey. So the 3, the number 3 has 4 neighboring cells. So we can't really do anything there. But the number 4 down here has 1, 2, 3, 4 neighboring cells, which means all of these guys have honey. And we already know that the 3 has the honey from the previous cell. So now we can look at the 3 and we know that, okay, out of the 4 bordering cells that it has, 3 of them already have honey, which means that this one up here does not have honey. So I'm going to give it a green, just to emphasize that that one does not have honey. So now, that 3 up there only has 3 neighboring cells, again, which means this one has to have honey. This 1 over here, on the end, out of its 2 neighbors, 1 of them already has honey, which means this one does not have honey. So the 3, it works because all of its 3 neighbors over here, the 1, 4, and the 2, all have honey, and the 1 does not. No honey there. And then the 4 in the middle has 4 neighboring cells that have honey, and 2 that do not. So this honeycomb is appropriately filled out, and we remember that the cells with honey are represented by the blue lines. And there are 1, 2, 3, 4, 5, 6 of those. So the answer is C6. Awesome. 2 more problems, and then we're good to go. Number 23. 3 girls, one after another, take some cookies from the tray shown. One of the girls takes all the heart-shaped cookies available on the tray. Another girl takes all the white cookies available on the tray. Another girl takes all the large cookies available on the tray. However, they do not necessarily take the cookies in this order. One girl takes 3, one takes 6, and one takes 7 cookies. Which of the following sets of cookies does one of these girls take? Okay, so let's write down our information. and we're gonna do it in a little table. So one girl takes all the hearts, one takes all the white, and another one takes all the large. One girl takes 3, one takes 6, and one takes 7. So let's see. How many heart-shaped cookies are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 hearts. And how many white cookies are there? 1, 2, 3, 4, 5, 6, 7. 7 white cookies. How many large cookies? 1, 2, 3, 4, 5, 6, 7. 7 large cookies. And we'll just check our work real quick. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So which of the following sets of cookies does one of these girls take? The girl who took 7 cookies could have either taken 7 of the white or 7 of the large. So let's pretend that it was 7 of the white cookies, which means that all of these are gone. Now, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9 hearts left. Well, that's not one of the options. That's not 3, 6, or 7. So we know that that can't be it. So let's see if the 7 cookies taken were the large cookies. 3, 4, 5, 6, 7. How many hearts are left? 1, 2, 3, 4, 5, 6. And there are 1, 2, 3, 4 white cookies. So let's X off the 6 hearts. 1, 2, 3, 4, 5, 6. And then finally, there are 3 whites left. So there were the 3 cookies. The girl that took 3 cookies was the one who took all the white cookies. The girl who took 6 cookies took all of the hearts. And the girl who took 7 cookies took all of the large ones. So which of the following sets of cookies does one of these girls take? Now all we have to do is compare the answer choices to either this set, or this set. Let's see. So one of the sets has 5 tiny black hearts and 1 tiny white heart. Nope. One set has 2. That doesn't work. Oh, look at this. E works, right? Because it corresponds exactly to this. 3 tiny circles. So this was actually quite a fun problem. It might look pretty big and daunting at first, but once you write down your information and solve it kind of in this table format, it makes a lot more sense. Also, always remember to count what you have up here. Okay, last problem. There are 2 types of blocks: white triangular prisms and red, they look like crowns. A small cube can be made using 4 white blocks or using 1 white and 1 red block. The larger cube shown in the picture is made up of small cubes. What is the smallest number of white blocks needed to make the large cube? So we want to minimize the amount of white blocks needed to make the large cube. So let's count how many white blocks we know for sure are being used. 1, 2, 3, 4, 5, 6, 7, 8. We can see those white blocks, and we know that since they're in this pattern, and the whole cube is white. So we know for sure that there are 8 whites. Now, this one, and this one there is obviously a red block, as you can see, which means that there is for sure a white block that accompanies them. So there are 3 white blocks. We know that for sure based on what we can see. So now, this is done, this is done, this is done, this is done, and this is done. How many cubes do we have left? This one, and then the one on the bottom back there. So that's 2 and 3. So we only have 3 blocks left, and we want to have the smallest number of white blocks, which means that the 3 blocks left have to be of 1 white block and 1 red block. And if you add all of this up, you get 14 white blocks in the minimum, and that is D. So for this type of problem, just make sure you keep track of what you're doing. It's actually not that hard of a problem for a 5-mark question, but you definitely need to keep track like this. My biggest tip is to not do anything in your head. I know that a lot of you are very, very smart and you can do it in your head, but the people who do it in their heads are also prone to silly mistakes. So always write down your rough work and you are bound to get a perfect score on the Math Kangaroo exam. So thank you for watching this video. Please come back for more. I will be solving other exams on this channel as well. So keep your eye out for those. Subscribe, and I'll see you next time.